Look at one of my favorite examples here. This is the integral of e to the minus x squared dx minus infinity. This is a famous integral. It gets wined and dined at parties and all that. This integral shows up in probability theory and in statistics and in physics. Y equals e to the minus x squared is the bell curve. And the bell curve is the basis of the so-called
So that integral is supposed to be 1.
okay, but it's not. But what happens is they monkey around with the exponent, they put a constant in the exponent, like minus alpha x squared, and they also monkey around with the outside, and so they put two constants in here that are rigged to where you do get 1 for the integral, and it tightens this up so that you get a certain value for the so-called standard deviation. I do not understand statistics. I'm okay at probability, and I don't really care to look at the Gaussian distribution. But anyway, we're just going to go with the straight one here. And the famous thing about this integral, one of the famous things, is that you can't work it out in terms of the fundamental theorem of calculus. Fundamental theorem of calculus, you need an antiderivative. And notoriously, this function does not have an easy elementary derivative, antiderivative. It's got an antiderivative because all continuous functions have antiderivatives. Until we get to the last chapter of calculus 3, in which case not all functions will have antiderivatives. But for functions of one variable, there's a difference between one variable and more than one variable. Functions of one variable that are continuous always have antiderivatives. But it cannot be generated in terms of add, subtract, multiply, divide, power, root, exponentials, logarithms, trig functions, inverse trig functions. Can't be done that way. And so, as far as calculus 1, 2, and 3 is concerned, we're screwed. Well, 1 and 2 anyway. But I'm going to work this integral for you using a neat trick. So, I'm going to call this thing, guess what I'm going to call this integral? I. And I'm not actually going to work on I itself. I'm going to work on I squared. And so that's
the whole
I.
integral?
What now?
The whole integral?
The whole integral squared. I times I. And so that's going to be this integral times the same integral. Except I'm not going to write it the same. I'm going to write it with y's instead of x's. Of course, you know it's the same result, right? So if I've got an antiderivative, if I've got like x squared dx, that gives me x cubed over 3. And if I have y squared dy, that gives me y cubed over 3. And those are different. You know, if x and y are different, then these two integrals are different. But if I make it a definite integral, if I go 0 to 3, let's say, that turns everything into a number, and I'm going to get 27 over 3 is 9. Guess what this will be? 9. All right. So these are equal. But the nice thing about having different letter names is that they are varying independently. So I can shuffle them. So I'm going to construct this. So I can take this one and move it inside.
Alright. I think I see what you're going with this.
Yeah. And then I can take this one and move it inside. And end up with this. So just like we've been taking intervals apart, all constant limits, integrams of product, we can take it apart. Well, these two, we can put them together. Take it apart, put it together, and then you make up his mind. All right.
So then on the graph, that would look like perpendicular bell curves.
Yes, it would. And a whole lot more. So, I mean, that's just in two directions. What would it look like if I went in the 45-degree direction? The same bell curve. The same bell curve. It's circularly symmetric. Why is it circularly symmetric? Because look what happens here. I can multiply exponentials by doing what?
Adding the exponent.
Adding the exponents. So I've got e to the minus x squared minus y squared, which I can factor that out and call it minus x squared plus y squared, which is r squared. And so yeah, it's circularly symmetric. So e to the minus x squared plus y squared dx dy minus infinity to infinity minus infinity to infinity. And you've already said it, it's r squared. Let's go to polar. So it's e to the minus r squared times
RD. And that's way easier to integrate.
Yes. In fact, this one's possible to integrate, this one's not. Because, you know, if I only had an x in here, everything would be wonderful. But I don't. I cannot make a substitution and make it come out doable. So now all I need is limits. So let's see, minus infinity, and y is going from minus infinity to infinity, and x is going from minus infinity to infinity. Oh, it's just a great big square. But in polar coordinates,
It's a great big circle.
it's a great big circle. All right, so theta goes all the way around 0 to 2 pi,
R is 0 to infinity.
and r is 0 to infinity. All constant limits, including the infinite limit. So we take the integral apart again. Again, he can't make up his mind.
This is a kooky problem.
It is a kooky problem. So anyway, equals the integral 0 to 2 pi. And I really like it when theta is not actually in the grand, because that makes that easy to do. And then this other one, e to the minus r squared r dr, 0 to infinity. And so now, u equals r squared, du equals 2r dr. I've got an r dr. So yeah, negative.
Yeah, you need to say u is equal to negative r squared.
Yeah, but then I'd have to worry with negative numbers. You can do it either way. But if you did that, then you'd have to change it to 0 to negative infinity, and you have to switch that around. I'd rather just do it this way. I'll have e to the negative u, and then this is just 1/2 du. Integrate that from 0 to infinity. And so let's see, the 2's cancel. And I get a minus e to the minus u from 0 to infinity. And we've got our pi out here somewhere. Pi where? I'm sorry, what?
Pi minus 1, pi plus 1.
Pi plus 1. is pi times this.
Oh,
Okay? So now I get, well, I'm going to get 0 for the right end, the infinity, because it's e to a negative power. So it's 1 over e to the infinity.
Minus negative.
And then minus a negative e to the power 0. So it comes out plus pi. But that's not the answer. That's the square root of the answer. Okay. So I equals plus or minus the square root of pi. My college algebra students would insist we've got to do plus or minus. Well, actually they don't insist on it here or that. But anyway, we know it's really plus because we're integrating a positive function in a positive direction. It's got to be plus. So the integral from minus infinity to infinity of e to the minus x squared dx equals the square root of pi. And when you look at that, you think, well, yeah, how could you possibly have an elementary function antiderivative? How could you possibly write down an elementary function that would give you the square root of pi?
Would it still work out even if your balance went from negative infinity to infinity?
So I mean, if I went like from 3 to 7,
Yeah, something like that.
it would not work.
It would not work.
Because when you try doing the same thing, here's 3 and 7, you'd be working on this square. And when you convert this to polar coordinates, it's still a square. And so you don't get all constant limits.
But if you set it up perfectly to like I don't know, some bounds that were like actual polar coordinates.
Well, like maybe from 0 to
1 maybe.
1, right, 0 to 1. Forget that I said that was 3 earlier. It's still not going to work because converting it to polar, see, that's going to give me an r equals secant theta and an r equals cosecant theta, and so I will not be able to separate the integers. Now you can do 0 to infinity, which just gives you half of root pi. All the mysteries of polar coordinates. Now,
And so the value of that integral is square root of pi,
yes, it is.
numerically.
And so when they make the adjustments to get a Gaussian distribution, then again, they multiply by something out here and they multiply by something on the x. And so those two, like an alpha and a beta, and those two together, they rig them where it comes out 1 because the total probability always has to be 1. But, I don't go there.
It was rigged from the beginning.
It was rigged from the beginning. It seems like there ought to be more than I need to tell you, but I don't think so. I will entertain another question if you want to ask me. Yes.
I was wondering what chapters you're going to be on this exam.
Well, let's see. Chapter 11, all, I guess, now. Chapter 12, we skipped some stuff. We skipped curvature for one thing.
Are you still going to do some of the some questions over the previous?
Math is cumulative. What can I say? So 12.5, arc length and curvature, you just do the arc length part in 12.5. 12.4, you, let's see, tangent vectors. To do the tangent vectors, you don't really have to worry about the normal vectors. 12.3, velocity and acceleration. I'm not going to ask you about that specifically, so you skip 12.3. So skip 12.3, skip curvature in 12.5, just do the arc length. 12.4, do the tangent vectors, but not the normal vectors. And 12.2, differentiation and integration. You don't have to integrate vector value functions, but you might have to integrate a magnitude of a vector value function, because that's that's the arcing interval. Okay, then, so chapter 11, we have now talked about the quadric surfaces, so 11.6. I'm not going to really ask you anything about it specifically, but we have covered all of chapter 11. Not cylindrical and spherical, we haven't done those two yet. So 11.1 through 11.5, you might go ahead and read through 11.6 again, but 11.7 you can skip. Then chapter 13, section 1 is just drawing the pretty pictures. Section 2 is limits, you can skip that. 13.3, 4, and 5. That was your basic partial derivatives. Don't forget the higher order partials, and don't forget that you can have a mixed second order partial. Then 12.4 is the differentials, the pre-chain rule section, and then 12.5 is the chain rule section. And that's as much as we've done in chapter 12. 13, we've done sections 1, 2, and 3. That's it. Let me give you a little bit of a maybe anecdotal history lesson here about this integral. Mathematician named, two mathematicians. One was named Liouville, French, of course, and another one was named Stokes. This is the only time you're going to hear the name Liouville in this course, but you're going to hear Stokes a lot in chapter 14. But anyway, I'm sorry, it wasn't Stokes, it was Thomson. William Thomson, also known as Lord Kelvin, was giving a lecture, and I think he didn't have a very high opinion of his students at that particular time, or maybe they were just giving him a lot of trouble with not understanding things and all that. Anyway, he got exasperated and wrote on the board, turned back to him and said, a mathematician is someone to whom that is as obvious as twice 2 makes 4 is to you. And he said, Liouville was a mathematician. So I don't know if he knew, I don't know if there's any association between Liouville and this particular integral or what. But anyway, I could even pull that quote out of the book I have. Let's see. But anyway.
Take attendance.
Gee, and I even was going to recycle last time's roll sheet. Yeah, I did it. All right.